But again, repeat again. In the next step, we will implement the Pythagoras theorem on this right rectangle OAM. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this right rectangle OAM, OA squared, that is the square of the hypotenuse, equals to AM square plus MO square. But again, in this right triangle AOM, according to the Pythagoras theorem, the following equation is true. OA squared, that is the square of the hypotenuse, equals to AM square plus MO square. OA equals to x, and therefore OA square is x squared, and it is equals to AM square. AM equals to 3 minus x, and therefore AM square equals to 3 minus x squared, plus MO square. MO equals to 1, and therefore MO square equals to 1 squared, that is 1. So in total, we should find out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. Here we have x squared on both sides of this equation, so x squared will get cancelled. After I cancel x squared on this side of the equation, we left with nothing, that is to say 0, while on the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we should find out that 0 equals to 10 minus 6x. Here we will add 6x to this equation, and get that 0 plus 6x is 6x, so 6x equals to 10. Here we will divide this equation by 2, and finally get that 6x over 2 is 3x, and it is equal to 10 over 2 is 5. So in total we should find out that 3x equals to 5. Here we will divide this equation by 3, and finally get that 3x over 3 is x equals to 5 thirds. That is to say, we have found out that the radius x of this circle equals to 5 thirds units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, the radius of our circle is x, and therefore the radius of our circle squared must be equal to x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 5 thirds, and therefore x squared must be equal to 5 thirds squared. So it is pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we should find out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 25 pi over 9 square units in size, so in terms of numbers, it is equal to 8.73 square units in size. And again, we should find out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 25 pi over 9 square units in size, so in terms of numbers, the area of this circle equals to 8.73 square units in size. So we finish with the second question. In the next step, I'll summarize the lecture. That is to say, I'll repeat on the solution of the first question. with the two methods, and then we repeat on the solution of this second question. Our task in the first question was to find out the area of this green shape. Actually, we found out the area of this green shape by using two different methods. So in the domain, we have quarter circle AOB. AD equals to DO and OB equals to 2. This is again DCB, this equals to 90 degrees inside, and therefore triangle DCB is a right angle, and therefore our task is actually to find out the area of this right green triangle DCB. This is actually the area of this green shape. AOB is a quarter circle, and therefore this is the angle AOB, this is the right angle. Likewise, OB and OA, they are both the area of the quarter circle. The radius of B equals to 2, and therefore the radius of OA must be also equal to 2 units in its length. The radius of OA has been bisected into two halves at point D. The first half AD must be equal to the radius over 2, that is to say it is 2 over 2, that is 1. The second half of the radius AO, that is DO, must be also equal to 1 unit in its length. In the next step, we implemented the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. So in this right triangle DOB, DB squared, that is the square of the hypotenuse, equals to DO square plus OB square. And again, in this right triangle DOB, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to DO square plus OB square. DB is the missing side, so leave it as it is. So it is DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total, we found out that DB square equals to 1 plus 4, that is 5. So DB square equals to 5. Here we took out of this equation, and found out the missing hypotenuse DB equals to the square root of 5 units in its length. This is the missing hypotenuse DB, that equals to the square root of 5 units in its length. In the next step, we did the construction, that is to say, we completed this quarter circle to a circle, and then we extended the radius BO by straight line until it touches the circle at this point. We define the touching point of the extended radius BO with this circle. This point is point P. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle, that equals to 2. BO is the radius of this circle, and therefore it is absolutely a straight line. When you extend the straight line by straight line, the result BP is also a straight line. But BP is a straight line that touches the circle, those 2 points B and P, and therefore BP is a chord. BP is a chord that passes from point O, that is the center of this circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of this circle. We extended the radius AO by straight line, and define until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. Point O is the center of this circle, point Q is the point of the circle itself, therefore Q is the radius of the circle, that equals to 2. For the same reason that PB is the diameter of this circle, AQ is the diameter of the circle. So both PB and AQ the diameters of this circle. In the next step, we extended side CD on this triangle DCB by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. We assume that the extended side CD will touch the circle at this point, point N. So according to our assumption, we have a periangle BCN. This is equal to 90 degrees in size, but periangle BCN is obtained on this chord BN. Chord BN is definitely not the diameter of the circle because of the fact that chord BN doesn't pass for point O, that is the center of the circle. Any chord that doesn't pass for the center of the circle cannot be the diameter of the circle. So we have here contradiction to rule 5. Why? Because we have periangle BC and it's equal to 90 degrees in size, and still it doesn't subset on the diameter of the circle because of the fact that chord BN is definitely not the diameter of the circle. Due to the contradiction to rule 5, we must conclude that the extended side CD will not touch the circle at point N. Likewise, we assume that the extended side CD will touch the circle at this point M. So according to our assumption, we have the periangle BCM. This is equal to 90 degrees in size according to rule 5, and still periangle BCM doesn't subtend on the diameter of the circle. Why? Because chord BM is definitely not the diameter of the circle. Why chord BM is not the diameter of the circle? Because of the fact that chord BM doesn't pass for point O, that is the center of the circle. Any chord that doesn't pass for the center of the circle cannot be the diameter of the circle. So we have contradiction to rule 5. Why? Because we have periangle BCM, this is equal to 90 degrees inside, and it doesn't pass, it doesn't subtend on the diameter of the circle because of the fact that chord BM is not the diameter of the circle. So due to the contradiction to rule 5, we must conclude that the extended side CD will not touch the circle at this point M. And therefore, we have to conclude that the extended side CD must touch the circle at point P and not in any other point. Otherwise, we will have contradiction to rule 5. Now we don't have contradiction to rule 5 anymore. Why? Because we have periangle BCP. This is equal to 90 degrees in size according to what is given as the question. And indeed, periangle BCP subtends on chord PB, that is the diameter of the circle. That is exactly according to rule 5. So this angle is right angle according to rule 3. Why? Because PB is a diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle PDO, the approach PD equals to the square for 5 minutes. It's 5 because 2 square plus 1 square is 5. So PD square equals to 5. And therefore, if we take the root of this equation, we get that PD equals to the square root of 5 minutes in its length according to the Pythagorean theorem. So in the next step, we implemented rule 24 in our drawing. So repeat quickly on rule 24. According to rule 24, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. In the drawing we have a circle, this is chord AB that intersects with this chord CD at point O. So whenever you have two chords that intersect with each other inside the circle, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. Well, because in our drawing, this is called AQ. AQ is the diameter of the circle. That is to say, it is the longest chord in the circle. So chord AQ intersects with chord CP at point D. Again, chord AQ intersects with this chord CP at point D. Why CP is a chord? Because of the fact that CD is one side of the line DCB, and therefore it is absolutely a straight line. When we extend the straight line by straight line, the result CP must be also a straight line. So CP is a straight line that touches the circle at those 2 points P and C, and therefore PC is a chord. So repeat again, we have chord AQ that intersects with chord CP at point D. Then again, code AQ intersects with code CP at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement rule 24. According to rule 24, the following equation is true: that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. Again, according to rule 24, the following equation is true: AD times DQ equals to CD times DP. AD is 1 times DQ. DQ is 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so leave it as it is, times DP. DP equals to the square root of 5 units in length. So in total, we actually found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to square root of 5 times DC. Here we divided the equation by square root of 5 and finally found out that the missing side CD equals to 3 over square root of 5 units in length. This is the missing side CD, this equals to 3 over square root of 5 units in its length. In the next step, implemented the Pythagoras theorem on this right triangle DCB. According to the Pythagoras theorem, in this right triangle DCB, dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. Repeat again, in this right triangle DCB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. dB equals to the square root of 5, therefore dB squared is equals to the square root of 5 squared, that is 5, and it is equals to DC squared. DC is 3 over square root of 5, and therefore DC squared is 3 over square root of 5 squared, that is 9/5 plus CB squared. CB is the missing side, so leave it as it is. So in total, we found out that 5 equals to 9/5 plus CB squared. Here we multiply it by 5, and then we divide it by 5 in order to overcome a factor with this number. So 5 times 5 is 25 over 5. 25 over 5 is 5. So in total we found out that 25 over 5 equals to 9/5 plus CB squared. Here we subtracted 9/5 from this equation, and we found out that 25/5 minus 9/5 is 16/5 equals to CB squared. Here we took out of this equation, and we found out that the missing side CB equals to the square root of 16, that is 4, over square root of 5 units in its length. This is the missing side CB, this is equals to 4 over square root of 5 units in its length. Our task is to find out the area of this green shape. The area of the green shape is actually the area of this green right triangle DCB. And again, the area of the green shape is actually the area of the green right triangle DCB. The area of this green right triangle DCB equals to the base DC times the height CB over 2. And again, the area of the green right triangle DCB in total equals to the base DC times the height CB over 2. DC is 3 over square root of 5, CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, square root of 5 times square root of 5 is 5 over 2. So the area of the green shape equals to 12 over 5 over 2. Here we move 2 to the denominator, so in total the value of this expression is 12 over 5 times 2. 5 times 2 is 10. So in total the area of the green shape equals to 12 times, that is actually 1.2. So if we found out that in both the area of this the area of the green shape is equal to 1.2 square inches inside. So we finish with the first method. In the next step, I will explain to you how to find out the area of this green shape according to the second method. So I'll repeat on the solution according to the second method. AOB is a quarter circle, and therefore this is angle AOB, that is a right angle. That is a right angle. Likewise, BO, OB, and OA, they are both the radius of the quarter circle, that is equals to 2. The radius OA has been divided into 2 halves at point D. So the first half of the radius AO is the length of the radius over 2. That is to say, it is 2 over 2, that is 1. The second half of the radius AO must be also equal to 1 unit in its length. So in the next step we did the construction, that is to say, we completed this quarter circle AOB to a circle. And then we extended the radius BO by sideline until it touches the semicircle at this point. We define the touching point of the extended radius BO with this semicircle. This point is point P. BO is a radius, it is absolutely a straight line. When you extend the sideline by sideline, the result BP must be also a straight line. So BP is a straight line that touches the semicircle, the 2 points P and P. Therefore, PB is a chord that passes for point O, that is the center of the semicircle, and we note that any chord that passes for the center of the circle or semicircle must be the diameter of the semicircle. So therefore, PB is the diameter of this semicircle. In the next step, we extended side CD of this line DCB by straight line until it touches the semicircle. According to the first method, we only found out that the extended side CD must touch the circle or semicircle at point B and not in any other point due to the contradiction to Rule 5. So the extended side CD must touch the circle at point B and not in any other point. Now we don't have contradiction to Rule 5 anymore because we have peripheral angle BCP, this is equal to 90 degrees inside, and peripheral angle BCP indeed subset on the diameter of the semicircle, that's actually PB. Okay, so this angle DOP is equal to 90 degrees inside according to Rule 3. So I'll not repeat on the same explanation. So in this right triangle PDO, 2 square plus 1 square equals to PD square, so PD square equals to 5, and we took out of the equation, and we found out that PD equals to the square root of 5 units in itself. In the next step, we define this angle PDPO, this angle is alpha, so in the right small triangle POD, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in any triangle. Likewise, in this big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that this is the small right triangle PDO that is similar to this big right triangle PCB. So why those two right triangles are similar to each other? First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you prove that all the figures of this small right triangle PDO correspond equal to all the figures of this big right triangle PCB. And therefore, those two right triangles are similar to each other according to angle similarity rule. So if you found out that the small right triangle PDO is similar, this is the sign of similar, to the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO over side PB of this big right triangle PCB is equals to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equals to side PO of this small right triangle PDO over side PC of this big right triangle PCB. And again, from the fact that the small right triangle PDO is similar to the big right triangle PCB, we will derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO over side PB of the big right triangle PCB is equals to side DO of the small right triangle PDO over side CB of the big right triangle PCB, and it is also equals to side P of the small right triangle PDO over side PC of the big right triangle PCB. PD is equal to 5, PB is 4, DO is 1, CB is the missing side, so we leave this as it is, PO is 2, and PC is equal to 5 plus DC. This is side PC, this is equals to square root of 5 plus DC. And again, PC equals to the square root of 5 plus DC. So in total, we should found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of this equation are equal to each other, so we can get the equation 1 from those two sides that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Repeat again according to equation 1, square root of 5 over 4 equals to 1 over CB. Here of course multiply the equation 1 and find out that 4 times 1 is 4 equals to the square root of 5 times CB. Here we divide this equation 1 by square root of 5 and find out that the missing side CB equals to 4 over square root of 5 units in its length. This is the missing side CB. This equals to 4 over square root of 5 units. This equals to 4 over square root of 5 units in its length. From this long equation, we derive that those two sides are equal to each other. So we get the equation 2 from those two sides that are equal to each other. So according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Again, according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here of course multiply the equation 2 and find out that 2 times 4 is 8 and 8 equals to the square root of 5 times square root of 5 plus DC. So again, according to equation 2, we find out that 8 equals to the square root of 5 times square root of 5 plus DC. So 8 equals to the square root of 5 times square root of 5 is 5, and square root of 5 times DC equals to the square root of 5 times DC. So here we subtracted 5 from this equation and found out that 8 times 5 is 3 equals to the square root of 5 times DC. Here we divided this equation by square root of 5 and found out that the limit inside DC equals to 3 over square root of 5 units in its length. This is the limit inside DC. This equals to 3 over square root of 5 units in its length. Now it is very easy to find out the area of this green shape. The area of this green shape equals to the area of this green times DCB. Because again, the area of the green shape, that is the area that we are looking for in this question, it is equals to the area of the green times DCB. And the area of this green times DCB equals to the base DC times the height CB over 2. Because again, the area of the green times DCB equals to the base DC times the height CB over 2. DC is 4 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 over 2. So in total, the area of the green shape equals to 12 over 5 over 2. We move 2 to the denominator of this expression. And so in total, this expression equals to 12 over 5 times 2. So it is 12 over 5 times 2. 5 times 2 is 10. So in total, the area of the green shape equals to 12 times. That is 1.2 square units in size. So in both methods, we actually found out that the area that we are looking for in this question, that is the area of this green shape, is equal to 1.2 square units in size. So we finish with the first question. The next step, I repeat on the solution of the second question. In the second question, our task was to find out the area of this circle. So the moment we have a circle that intersects with this right angle ACP at those 2 points. In addition, we know that this is line 7BC, this is equals to 1 unit in its length. This is line 7CP, this is equals to 4 units in its length. In addition, we know that in relation to this circle, point P is the common standpoint. From the common standpoint, point P, we have 2 tangents to this circle, tangent PA and tangent PB, and according to 2, they are equal to each other. Again, from the common standpoint, point P, we have 2 tangents to this circle, tangent PA and tangent PB, and according to 2, they are equal to each other. So if we focus on the common standpoint, point P, we have 2 tangents to the circle, tangent PA and tangent PB, and according to 2, they are equal to each other. This is to say PA equals to PB. But it is given us the question that the length of tangent PB in total is 4 plus 1, that is 5. So we can write here that tangent PB equals to 5 units in its length. And from this equation, PA equals to PB equals to 5, we derive that tangent PA must be also equal to 5 units in its length. This is tangent PA. This equals to 5 units in its length. In the next step, this is angle ACB, this is right ACP, this is equal to 90 in size. So in the next step, we implemented the Pythagoras theorem on this right triangle ACP. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. But again, the right triangle ACP, according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and it is equals to AC squared. AC is the missing side, so leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, we actually found out that 25 equals to AC squared plus 16. Here we subtracted 16 from this equation, and we found out that 25 minus 16 is 9, so 9 equals to AC squared. 9 equals to AC squared. Here we took out of this equation and found out that the missing side AC equals to the square root of 9, that is 3. So this is the missing side AC, that is equals to 3 units in its length. In the next step, actually, PB is a tangent to this circle, so PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point C, here the sum of the areas must be equal to 180 degrees according to all three. So we can guess we have at the upper side of the straight line PB at point C, we have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 9 degrees in size. So in the next step we define the center of this angle, this point is point O, and we find the radius of this angle as x. And we join points O and B together by straight line. Point O is the center of this angle, point B is the point of the circle itself, therefore OB is the radius of this angle, that is equals to x. The radius of B is equals to x, the radius of B is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever your radius is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say from point O, that is the center of this angle, we do perpendicular on AC. From point O, we do perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and AC, this point is point M. By doing this construction, we can deduct quadrilateral OMCB. In quadrilateral OMCB, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth angle, in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth angle must be equal to 90 degrees in size. So in quadrilateral OMCB we have 4 angles, and therefore quadrilateral OMCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM, but BC is 1, therefore the opposite side OM must be equal to 1 unit in itself. Likewise, according to the sum rule, the sum of rectangle OMCB, side OB must be equal to the opposite side MC, but OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this missing line set AM? From the drawing, it is very easy to say that AM in total equals to AC minus CM. Again, AM equals to AC minus CM. So AM equals to AC, that is 3, minus CM, that is x. So in total, AM equals to 3 minus x units in its length. In the next step, we join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that is equals to x. In the next step, we implemented the Pythagoras theorem on this right triangle OAM. In this again right triangle OAM, OA squared, that is the square of the hypotenuse, equals to AM squared plus MO squared. Because again, this right triangle OAM, according to the Pythagoras theorem, OA squared, that is the square of the hypotenuse, equals to AM squared plus OM plus MO squared. OA is x, therefore OA squared is x squared, and this equals to AM squared. AM is 3 minus x, and therefore AM squared is 3 minus x squared, plus OM squared. OM is 1, therefore OM squared is 1 squared, that is 1. So in total, we should find out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, that's 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of this equation, so x squared we have said. After we have said x squared, in this side of the equation left with nothing, that is to say 0. Well, on the other side of the equation, we have 9 plus 1, that is 10, minus 6x. So in total, we should find out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and find out that 6x equals to 10. Here we divide this equation by 2 and find out that 6x over 2 is 3x, and it is equals to 10 over 2, that is 5. So in total we found out that 3x equals to 5. Here we divided this equation by 3 and found out that x, that is the radius of this circle, is equal to 5/3 units in its length. Our test is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, and therefore the radius squared must be equal to x squared. So in total, the area of our circle must be equal to pi x squared. But x is 5/3. If x is 5/3, it means that x squared must be equal to 5/3 squared. So in total, the area of our circle must be equal to pi times 5/3 squared. So it is pi times 5/3 squared. 5/3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area that we are looking for in this equation, that is the area of this circle equals to either 25 pi over 9 square units inside. So in terms of numbers, the area of this circle equals to 8.73 square units in its size. Okay, thank you very much.